In this question, we've been told that a discrete random variable x has a probability distribution where x follows a Poisson where the parameter is lambda. We've been asked to derive from first principles the probability generating function of x. We're just going to state here, x follows a Poisson with lambda. If we're going from first principles, we're going to need to make use of the probability function. So that's e to the negative lambda, lambda to the power of x, all over x factorial. Going from first principles, we're almost going back to a discrete random variable. We're going back to a probability distribution for the Poisson. So we need some outcomes, the x values, and we need some probabilities of these things happening. So the probability that x equals 0, that's going to be e to the negative lambda, lambda to the power of 0 over 0 factorial. The probability x equals 1, e to the negative lambda, lambda to the 1 over 1 factorial. Probability equals 2, e to the negative lambda, lambda squared over 2 factorial. And I hope you can see that this is going to continue for every integer value that we work with. I know this pattern continues, so I don't need to write out anymore. A probability generating function is going to be the sum of the probability as a coefficient, t as a dummy variable, and x as a power of that variable. So we're just going to make this sum for each of the corresponding x values and probabilities. So that's e to the negative lambda, lambda to the 0 over 0 factorial, t to the 0. Probability of 1 times t to the 1. Probability of 2 times t to the 2, and the probability of 3 times t to the 3. Once again, it's a pattern that's going to continue. What can we do to simplify? I'm going to factorize out a common factor, e to the negative lambda. I'm left with something smaller inside the brackets, but it should be looking familiar. I now notice that both lambda and t have the same power in each term. So let me actually just factorize those, write those in a bracket, and apply the power to them. And now we should be noticing this pattern. I have a value to the power of 0 over 0 factorial, bracket to the power of 1 over 1 factorial, bracket to the power of 2 over 2 factorial. This you should recognize as the Maclaurin expansion of the form e to the x. Now this is something I want you to recognize, but it is also in the formula book for you to refer to. But if you've asked to derive something from first principles, I'm hoping that you can tell what to expect and to be aiming for a certain situation. Okay, so usually this would be x to the 0 over 0 factorial, x to the 1 over 1 factorial. So instead of e to the x, we're going to have e to the lambda t. So e to the negative lambda times e to the lambda t. Okay, writing that as one term, e to the lambda t minus lambda, and then we can factorize out lambda. And this is the standard result for the probability generating function for x if x follows a Poisson distribution where the parameter is lambda. Now, these standard results are given in the formula book, so you do know the end point of where you should be getting to, but first principles, we need to start from a probability distribution and follow the general format for a probability generating function. In part B of the question, we're asked to use gx of t to show that the mean and variance of x are both lambda. Okay, so the way that we use a generating function to calculate the mean, we know the expectation is g dash with 1 substituted in. Let's get an expression for g dash of x. We're going to differentiate. I bring down the derivative of the power, so that's just going to be lambda, and I multiply it by e to the lambda t minus 1. Now, I'm going to substitute t equals 1, and we get a power of 0 over here, meaning e to the 0, which is 1, which leaves us with just our lambda. The expectation of x is lambda. The mean of x is lambda. Let's see if we can do a similar thing for the variance. To find the variance, we're going to need to find g double dash of x. So, differentiating one more time, we're going to get lambda squared e to the lambda t minus 1. And if we substitute in a 1, we once again get a 0 power on the exponential, leaving us with lambda squared. The variance of x, well, that's going to be g double dash of x with a 1 substituted, plus g dash of x with a 1 substituted, minus g dash of 1 squared. Substituting each of these, we can see that it all falls away to leave us with just lambda. So what a nice way to show that both the expectation and the variance are both going to be lambda. In part C of the question, we've been asked to use a method involving generating functions to show that the expectation of x plus y equals lambda plus mu. So let's start off by defining both the distributions. X is a Poisson with lambda and y is a Poisson with mu. W we're going to call a combination of x plus y, w. Now, in terms of generating functions, the probability generating function of w is going to be the probability generating function of x multiplied by the probability generating function of y. We should have an expression for each of those. So, substituting in e to the lambda t minus 1 multiplied by e to the mu t minus 1. Using index laws, we know we can expand and add together the powers. And just to tidy up, I can factorize out t, and I can factorize out -1. One more step of factorizing, lambda plus mu, t minus 1. So this is the probability generating function for w. The expectation for w, I can differentiate and substitute in 1. When I differentiate my probability generating function, I get lambda plus mu as the constant, which comes down to be part of the coefficient, and e to the lambda plus mu, t to the minus 1. We should be getting used to this now. When I substitute in 1, the power on the exponential becomes 0. So I've got e to the 0, which just leaves me with lambda plus mu. So the expectation of w is lambda plus mu. Let's not forget that lambda is the expectation of x, and mu is the expectation of y. And we know that they together will be the expectation of x plus y. So the expectation of x plus y equals the expectation of w, which equals lambda plus mu.